So hello everyone, this is lecture 19 for the quantum mechanics. In the last lecture we were discussing about the Dirac notation. So I told you what are cat and bra notation. So in the cat you write the column vector and bra is just the complex conjugate and means that is also the transpose. So you will take the dagger, then dagger of cat will give you bra. So that's how we defined this, and I told you that how you can write your wave function in terms of cat and bra notation. So cat can be written in this form. So this is also vector and these are also vectors. So this can be written in some of these. Now you can write this wave function in the terms of bra also. So how you can write this means just take the dagger of all of them. So dagger of this will give you C1 conjugate, and this is bra of phi1, and for the bra of phi2 and C2 star, and here also it will give you this bra of psi. So that's how you can write in terms of this also. So these represent the same thing, and I told you what is the inner product. So for the two wave functions, so that is this. Now if the inner product came out to be 0, we will call the functions as orthonormal or orthogonal functions. So that was we discussed in the last lecture. So today we will understand some more basic things, because without them you won't be able to understand the quantum mechanics. So let's first understand the matrix. Hope you know about the matrix. So let's see what you don't know about the matrix. So some matrix is written in this form. So what is the meaning of this? So matrix is nothing but a operator. Okay, it is an operator, as I told you in the mathematical physics also, when we were studying about the rotation motion, means rotation matrix. So there I told you that when you apply some matrix on some vector, then it will gonna rotate that vector in the 2D plane. So that is the same thing we will study here. So let me revise that for you. So this matrix operates in the 2D space. So this matrix is nothing but it's kind of operator. So that will operate on a particular column vector and it will gonna change that. So like this, if you have some column matrix in the rotational matrix and this is your vector, and you apply that matrix on this vector, so this will gonna change to this. So this kind of when you apply some matrix, so this matrix is called the transformation matrix. Okay, and now see, this matrix can transform your complete vector space also, and that can be in the linear transformation also and the non-linear also. So when we call that linear and when we call that non-linear, so let's see, a transformation is linear if it has two properties. So to make it linear, these two properties must be satisfied. So first is all lines must remain lines without curve. So when you apply this transformation matrix on the vector space, so when the new space will created, that space should not have some curved lines. So if it is first you have this square, so next should also be some straight lines also. Means let me show you this thing. If you have this kind of curve and you apply the matrix, these are all the straight lines. So this can't be in this way. So this next space you get, this is not a linear transformation, but it can be converted into some sheared or some sheared stress, or this can be changed to this, and it can be these distances can be varied very easily, but they should be straight line always. Then we call that this transformation is linear, this transformation is also linear. So this can be at some angle also. Okay, this not need to be perpendicular always. So this can be some tilted angle, and that is also a linear transformation. And second condition was that origin remains fixed in place. So origin must not change. If you have origin here and you change this to this, so origin must remain there, and this can be tilted. So but origin must remain same and the line should be straight line. Then we call this as linear transformation. And let's see now some more visual examples. Let me tell you, if you have you have this xy plane. So I will tell you about the rotational matrix. So if I rotate this xy plane like this, means this x will came this side and y will go upside. Means it is like this is I and this is j, and the j will go this side and I will go upside. So we'll rotate this complete plane to the 90-degree anti-clockwise. Now see what is your new ij. So in the old coordinates, so now this new j will be minus I cap plus 0 j cap, and this I will be here, and this new I is nothing but 0 I cap plus I j cap. So if you write this in the matrix form, it will be 0 1 minus 1 0. So new I is nothing but here it is minus I and 0. So new I is here 0 I plus ij, and new j is here minus I plus 0. So minus 1 0 and 0 1. So this is your transformation matrix for this rotation, for the 90-degree rotation. Now if you take any vector in this space and you apply this matrix or operate this matrix on that vector, that will also rotate by the 90-degree angle, and that will be changed to the new space. So let's see, if I have this vector r, and this is your x and y, and r is this 1 I cap 1 j cap, and you applied this matrix on this. So it will be this 0, 1, minus 1, 0 and 1, 1. This will give you minus 1, 0, minus 1 and 1. So now first this vector was 1 I cap 1 j cap. Now it will be minus 1. Minus 1 will give you minus I and plus 1 j. So it will be here. So this will change to this. Now see, we are having the same thing as we are having here. So this matrix represents the rotational matrix now. Means any vector in this space, you will this matrix will be applied on it. That will change to the rotational plane. Okay, means to the new plane. Same you can find about this Q also, for this P also. So you just apply this matrix, multiply that, and you will get the new vector in the new space. So that's how. Now see, this space need not to be only perpendicular, means you are just rotating it. So you can rotate it to the plus clockwise also. So let's see, if we rotate it clockwise, then what will be your transformation matrix. So now this I will go here and J will go here. So J, new coordinate for J will be 1I plus 0j. So for the new it will be, and see this x is in the this direction. So new vectors for the I is nothing but minus 0x and 1 minus 1j. So it will be 0 minus 1, and for the j it will be here. So j will be 1 I cap plus 0 j cap. So it will be 1 0. So this is transform matrix for the clockwise direction, 90-degree angle. Now if you apply this on this vector, so this vector will be in this direction now. So you will apply this on the 1 1, then you will get what? You will get 1 minus 1. So that's how you can see that how can we transform these things, transform the vector, and what is the transformation matrix, and how we call that a matrix is a operator. Now you can find this new matrix for any theta, means this need not to be only 90-degree. This can be 45-degree, 40-degree. So at any angle you can find the matrix, and that will operate in any vector. Then it will give you the new vector in the new space. If you have the 40-degree, then this space will tilt it to 40-degree. Then this new space will be formed, and you apply the matrix on the vector in this space. This will give you a vector in the new space. So that's how this matrix works. Now let's see some more interesting things. Now this need not to be always 90-degree, so we can take the shear also. So let me tell you what is the shear transformation. Now let's say this transformation, like only the j is rotating, means we rotated j by 45-degree and I is as it is. So what is the transformation matrix for this? So see, now new ij will be, for I it is same 1 0, and for the j, new j will be 1 1 at the 1 1 position. So we'll take the coordinates in the old and for the new one. So j will be in the 1 1 and I is 1 0. So this is your transformation matrix for this. Means first plane was your this, first vector space was this, and next vector space now is this. This has tilted angle. So this is your next vector space. So as I told you here, you can transform this vector space to any space. So that's how you can do that. You can change the ij to new ij. So now new j is at 45-degree to I, and this can represented by this. Now if you operate this matrix on any vector which is in ij, so that will give you the new vector in the this ij dash. So let's see, if we apply this 1 2 here, so this will give you 3 2. Okay, means it is 1 and 2, this vector is here. Now it will be 3 2. So it will be 3 and 2. So this will give you here. So this is just sheared here, sheared to the right side. So that's how now this is your new transformation matrix for this kind of a space, means from the this ij space to ij dash space. Same, you must know that in the matrix system, the product is not the commutative, means AB should not be equal to BA. So let's see why it is that and why it can't be equal. So here you can see that if we have some vector R, and if you take the ST of R, means first you will apply this transformation matrix for the rotation matrix. First you apply this on the R, so it will rotate to the 90-degree left hand side. Now if you apply S after that, so it will give you shear. So whatever you will get here, so first apply the T on the 1 2, then apply this S on the next one, so you will get minus 1 1. But now you will apply T as R, means first you will apply S, then you apply the T. So first you will take the shear, and then you will take the transformation, rotation transformation. So that will give you a different vector, minus 2 3. So see, they are not equal. That's why we say that in the matrix form, this product rule means matrix are not commutative. ST should not be equal to TS. So that is the reason, because we don't get the same thing. So that's why operators should not be commutative. Now this was the meaning of matrix. I hope you understand what is the transformation, how we do that. Let's see now the meaning of determinant. You know already how to find the determinant, what is the meaning in the maths only. But now we'll see what is actually determinant is. So if you have something like this, so this is your transformation matrix. Now what this represent, you take the determinant, it will be 1. So what this represent, it represent that in the new vector space you are getting, the area will remain same 1. Means this is the expandation of the ij vector. This represent the expandation of the area. So in the first space it was 1 0 0 1. So it was, you can see from here, it is 1i and 1i and 1j. So area is this. Now the new vector is 1i 1 0, this is same, and second one is 1 1. So it will be here somehow. So this is your new. Now if you make the area, this will be this for the old one, and new area will be this parallelogram. Now both have the same area, because you know the property for the parallelogram and the square. This area and this area will be same. So that is representing here, means determinant of this is giving you 1, means area will remain same in the new vector space also. Let's see for this one. New transformation is 3 0 0 2. So if this is your I and j, so I will change to 3i and 0j. So it will be 1 2 3 here, and j will change to 0 2. So 0i and 2j. So it will be here. So this will be your new vector space. Now see, first area was this. Let's say it is 1 unit, and now you have this complete area. So this will be 6 unit, 3 3 6 unit. So determinant is 6 here. You can see that. So now this area represents the how the area will expand in the new vector space for the unit vectors. Now let's see for this 4 2 2 1. So if you find the determinant here, it will give you 0. So what is the meaning of this? That there is no area in the next vector space or not? So let's see, visualize this. It is 4 2, means 4x and 2y. So it will be something like this. And the next is 2 and 1. So it will be, let me correct, it is 4 to I, means I is new I is 4 2, means this is 4 and this is 2. So this new vector will be I. So this is I dash, this is I dash. Now see for the j is 2 1. So it is 2 and 1. So this will be your new j. So I and j are in the same direction, you are seeing that. In the new vector space, I and j will be in the same space. And now see, the area between them will be 0. So they will squeeze the area to 0. That's why we are getting this 0, because there is no area between two lines which are parallel. So that is the reason. So this determinant gives you the expansion of area. Now if you get some determinant minus 3, so what is the meaning of that? So minus represent that your matrix is just reversed, means here you have the j, you have I, but in the transformation you will get here j and here I. Now you see, if you can rotate it anywhere, this will always remain, I will remain on the left hand side of the j, and j will be this side. So this is, any area here will be in the minus, because this is just flipped down. Okay, this is flipped the area, or the vector space is flipped. So that's why we are getting negative here. Now what is the meaning of inverse in the operation? So see, inverse is nothing but, it's like you have t that is rotating 90 degree anti-clockwise. So t inverse will be rotating your matrix or the vector in the clockwise 90 degree. So this is your matrix for the 90 degree anti-clockwise, and this inverse will give you operator which is the matrix operator, which will operate and means rotate the vector to the 90 degree clockwise. So first you will get anti-clockwise direction, then it will be clockwise, so it will be remain as it is. So that's why we can say t inverse t will give you your same vector, that will not change anything in that, because that will remain at the same place. So I hope you understand this thing. This is very easy. Now you know about the rank from the mathematical physics. I told you about this. So rank is nothing but, you have the non-linear equations. So you will see that how many rows you have which are non-zero rows in the matrix, that will give you your rank. Means here you have these two rows, and you can't make both any one row completely zero. So if you subtract this one from this one, it will get you 0 1 here. So again you have non-zero number here and non-zero here, so it will give you 2 rank. But here you can subtract this from this, it will give you 0 0 here and 1 2 here. So only one non-zero row you have, so rank will be 1 here. So what this rank represent physically now, means this is just the mathematical thing. So rank represent in the quantum mechanics that how the space will be squeezed. Means if you have some space, then this matrix will squeeze that space into the 2 dimension, and here it will be squeezed to the 1 dimension. So see, if you see this new vector space with this operation matrix, you will see that it will come to the single line, as we did here, because these both were parallel, and that's why they squeezed your space to the one dimension. Squeezed, okay, that was the correct term. Now you can find for this also, this is 3 into 3, so this will be in the 3 dimension. So I hope you understand this rank term in the matrix, and now you understand the matrix much better way, that what is matrix and all. Let's see one more thing for today, that is the last thing for today, that is eigenvalues and the eigenvectors of a matrix. Now what is the meaning of them? From the mathematical physics, you know how to find eigenvalues, how to find eigenvectors. So you will apply Ax should be equal to lambda x. Here lambda represent the eigenvalues, x represent the eigenvectors, and you know how to find them. But let me tell you what is the meaning of them, physical meaning. So if you apply some matrix on an eigenvector, so that will change this vector only the magnitude of this vector, means this will not change the direction, and it will change its magnitude to the value which is its eigenvalue. Means if you have this minus 1 1, so this will be here. Now this when you apply this matrix on this, so it will give you eigenvalue is 2, so it will be 2 times the initial vector in the same direction. So that is the actual meaning. Okay, means for the any matrix it is 2 into 2 order, so you will get 2 eigenvectors and 2 eigenvalues. So there will be 2 vectors possible in this space, on which if this matrix operate, then it will change only the direction, only the magnitude, not the direction for the vector. So there is only 2 vectors possible, that is eigenvectors for this matrix, which will change only its magnitude when this matrix apply on them, and magnitude will be changed to the value which is eigenvalue. So it will change to 2. So the vectors whose only length increases after transformation are eigenvectors. 2 is the eigenvalue, that's why it changed to 2 when this matrix applied on this. And you can find easily how to find the eigenvalues. It is nothing but a minus lambda equal to 0. So you will subtract them and put this determinant equal to 0. Lambda will be 2 and 3. So for the 2 you get this minus 1 1 as your eigenvector. For 3 you will get 1 0. If you find, you will get the same eigenvector. Now this is the second eigenvector exists. Now you operate this matrix on the 1 0. You will get a new vector 1 0, and that will change to, that's magnitude will change to 3. Means if it is 1 0, 1 0 will be like x1 y0, so it will be here. Now if you apply the matrix on this vector, it will change to 3 times this. It will be 3 times this and the same direction. So that is the meaning of eigenvector and the eigenvalues. So we will use these things, eigenvalue, eigenfunction, eigenvectors, eigenstates, in the quantum physics. So it's like you will operate some operator. So any operator, just like you have this matrix, so any operator in the quantum mechanics can be represented in terms of matrix, and that will operate on the wave function and give you some value, that is eigenvalue, and change the function. Means its direction will not change, but it will give you some value how this function is changing. So just like you operate a matrix on the R vector, same you will operate your quantum operator on the wave function, and you will get your eigenvalue and the eigenvector. So we'll see how these eigenvectors and the eigenstates are helpful for us. So we'll meet you in the next lecture. Thank you everyone.